Today we'll study about longest common subsequence. So here we are given two sequences and we have to find a common subsequence having largest possible size. So first we define what we mean by a sequence, then what is a subsequence, what is a longest common subsequence, and then we'll see that finding longest common subsequence brute force algorithm takes exponential time. Then we'll design a dynamic programming algorithm which solves only in quadratic time. So first we define a sequence. So a sequence we can define it as an ordered n tuple. Simple example of a sequence, we can take this X A B C B D A B. This is example of a sequence. So sequence we use this notation, angled brackets, and we follow the examples and algorithms in the textbook by Corman, Lizerson, Rivest and Steen, Introduction to Algorithms. Next we define a subsequence. So for defining subsequence, suppose we have a sequence. So given, we define this as given a sequence, call it a capital X, sequence of length m, x1, x2 up to xm. Another sequence z, another sequence z, and having k elements, z is equal to z1, z2 up to zk, is a subsequence of x if there exists a strictly increasing sequence. Sequence Z is a subsequence of F if there exists a strictly increasing subsequence. There exists a strictly increasing sequence of indices I1, I2 up to Ik, sequence of indices of X such that for all J is equal to 1 to up to K, we have Xij is equal to Zj. So what this means? So we should have a sequence of this ordered sequence of indices strictly increasing, so that you can find the elements of Z within this X. Then Z is called a subsequence of X. So this is the definition of a sequence. and a definition of a subsequence. Now, same example we take and several examples of subsequence. So once again, taking the same example, suppose x is equal to a b c b d a b. We start with this sequence. Now there are several possible subsequences. We can have empty subsequence of any single letter A, B, and so on, C, D. These are subsequences of length 1. This is subsequence of length 0. Now subsequence of length 2. So we can have BB. BB, how you get? This B and this B. So you should be able to find this within the original sequence in the same order. More examples. We also have BA, like this, BA. We also have, these are subsequences of length 2. Yes. No. So there is only a single. This is separate. This is a subsequence. So you can in several ways find the subsequence within X. So but they are counted only once, not multiple times. So just make this distinction.
So why is it counted once when there are like 2 in the whole sequence?
No, just see. This is a subsequence. Now, how you can multiply this several instances? You are given a subsequence. This is of single count, not multiple count. So you can find, you may be able to find it as a subsequence in multiple ways. So it does not matter. What matters is we have a single subsequence that you can find within X. So in the definition you see, the only requirement is we should have this condition satisfied. Nothing else. Nothing is described that about particular order like this, if there exists. So here existence, just existence is sufficient. No need to find the multiplicity, how many instances are there. Just if it exists, then we say that it is a subsequence and it is counted once. So just remember this. So we continue with our example. Next subsequences of length 3, we have BCB, PCB, how we get? BCB. Next we also have subsequences of length 4, like this, BCBA, BCBA, and also we have BDAB. Now we see BCBA, how we get? BCBA, and also BDAB, we get BDAB. So these are subsequences of length 4. Now more than 4 is not possible. Subsequences of length 5, no, it is for common subsequence. So we can continue like this. Subsequences of length 5 also we can find. Several examples we can have, like AC, D, AB, and also subsequences of length 6. Simple example, BC, B, D, AB, and also subsequence of length 7, X itself, ABC, B, D, AB. So we defined subsequence. Next we define common subsequence. So for common subsequence, suppose we are given two sequences X and Y. Given two sequences x and y. So we say that a sequence Z is a common subsequence of x and y if it is a subsequence of both. So this Z, it should be a subsequence of x as well as y. Then we say that it is a common subsequence. So this is definition of common subsequence. So again we take simple example and see several examples of common subsequences. Take for example x as ABC BDAB, and take y as BDC ABA. Now we can find several examples of common subsequences. So starting from smallest size to the largest possible size. So, common subsequences. So ordered by size. So size 0 we have empty. So empty subsequence is always a common subsequence of any two given sequences. Then of length 1, the single letter, it has to be in both. So A is in both, B also, C also, D also. So A, B, C, D. Next, common subsequences of length 2. So some examples can be BB. So BB, we can see BB is in X, BB is also in Y. And also we can have several examples of size 2, just taking one representative. Another of size 3 we can take BCB. BCB. So X we have BCB and for Y we have BCB. Next of size 4. So size 4 we have two examples, BCBA and BDAB. So first BCBA will verify. BCBA, here also BCBA. Next is BDAB. BDAB, here also BDAB. So this is the largest possible we can get. 5 is not possible, of length 5. So 5 you can verify taking all possible combinations. So length of Y is 6. So you have to skip one element. If you skip B, we get DCABA. DCABA you will not get here. Similarly, if you skip D, we get BCABA, BCAB. We are getting BCAB. Next, if we skip C, we get BDABA. BDAB. Skip A, BDCBA, BD. Skip B, it is BDCAA, BD. skip A, B, D, C, A, B. So we have verified all possible combinations, six possibilities of subsequences of length 5 in Y, and we have verified that it is not a subsequence of X also. So 5 and above is not possible. So the largest possible subsequence that we can get is of length 4, and at least 2 examples are there. So we define the longest common subsequence as, simple definition, LCS, longest common subsequence of X and Y, is a subsequence, is a common subsequence. Common subsequence of X and Y having largest possible length. So we define LCS, longest common subsequence. Now the LCS problem is given 2 sequences, find their LCS. So the LCS problem, simple. Given 2 sequences, call them X and Y. Let X be X having M elements, x1, x2 up to xm, and Y is equal to y1, y2 up to yn. Find an LCS. Call it Z. Z1 up to Zk. We do not know what is the value of k. We will determine LCS of X and Y. This is the LCS problem. So first we consider this brute force algorithm. So brute force algorithm, what we do is simply try all possible subsequences in one sequence and check it for the other sequence. So we'll see that it takes exponential time. So brute force algorithm. Here generate all possible, enumerate, generate all possible subsequences of say X. Then for each generated subsequence, call it xi of X, check if xi is also a subsequence of Y. So this we have to do. So first generate all possible subsequences of X. This is first step. While doing this, what we do is for each generated subsequence xi of X, we also check that if it is a subsequence of Y. So so we can make a for loop, generate all possible subsequences of length X, and within the for loop, for each generated subsequence xi of X, we have to check if xi is also a subsequence of Y. And here we just keep track of lengths of xi and also the LCS length. So just keep track of the length of LCS and also this xi. So this is brute force algorithm. Now how many possible subsequences of x we can have. So x we can see it has m elements. So if we have to take each element, either we take or we do not take. So we have two possibilities, and for m just take the product, we get 2 to the power m. So there are 2 to the power m possibilities. So this enumeration we get 2 to the power m elements. Now once an element xi is generated, to find that if it is it is also a subsequence of y, we have to scan y also. We have to scan y. So y is of length n. So it will take in the worst case n time, and also we have to scan xi also. Xi can be a maximum of length m. So this is the upper bound on the complexity. So just multiply the two, we get time complexity as T1n, we can T1n m we can write big O of 2 to the power m n plus m. So we are getting exponential time complexity. So now we'll improve this to only quadratic.
So
Yes.
calculate the time complexity. Like, where did the n plus 1 come from in the expression?
Yes. So
Comparison? Matching?
yes, matching. So for matching, you have to scan both. You are scanning y start to end, so it takes time n. In the meanwhile, you are also scanning the xi for matching the individual elements. So what is upper bound? Upper bound is m. So both you have to keep track of both. You are scanning y as well as xi.
So that m is the minimum of x and y.
No, m and n are given here, not minimum, maximum. M is of length x, y is of length n. So out of x and y, you can choose which one is the minimum and enumerate that. So in the complexity, you can improve this to minimum of 2 to the power minimum of m and n. So better we can write optimized time complexity big O of 2 to the power minimum of m and n multiplied by n plus m. This is optimized time complexity. So now we designed dynamic programming algorithm and improve the complexity to only quadratic. So this we will reduce to big theta of m n. Time complexity, call this T2 n m, and also space complexity will also be similar S2 m n. Also we have to make table space complexity. So now, yes. So now first step in designing dynamic programming algorithm is find the optimal substructure of LCS. Optimal substructure. So for optimal substructure of LCS, first we should identify the subproblem. So subproblem we define as the prefix. Define the subproblem. So these are prefixes of the original problem. So we define prefix as given a sequence take x1 up to xm. We define the ith prefix. We define the ith prefix, call it xi of x. Yes, just take the prefix x1 up to xi, and here I can range from 0 up to a maximum of m. So for 0th prefix is empty subsequence, otherwise xi is start from x1 go up to xi. This is ith prefix. So these are the subproblems we'll take, and Just a very simple example. Take this X as ABC BD AB. Then X4. X4 is 1, 2, 3, 4. A, B, C, B. X0 is empty. And so on. So now using these prefixes, we consider optimal substructure of LCS. So now there are two possibilities. We compare the last elements of both X and Y. The two possibilities are they are same and they are not same. So in both cases we'll have some slightly different structure. So now we write the optimal substructure. So let x1 up to xm and y1 up to yn be sequences, and let z is equal to z1 up to zk be any LCS. So same notation we are using. X is of length m, y is of length n, assuming LCS is of length k. So first we compare the last elements. So last elements of x and y. These are xm and yn. So there are two possibilities. They can be same, they can be different. So if they are same, then first possibility is they are same. So first we write if xm is equal to yn, then zk is equal to the same. Xm is equal to yn and zk minus 1 is an LCS of xm minus 1 and yn minus 1. So this is our first observation, that if the last elements match, then last element of LCS should be the same, and what is remaining is the prefix zk minus 1. It should be an LCS of xm minus 1 and yn minus 1. So this is a very simple observation. Suppose LCS, in LCS it is not the common element. It means in the LCS we are taking elements before xm and before yn, but xm and yn are same, so we can safely append it and increase our LCS. So contradicting the fact that z is an LCS. So with this observation we should have last element of z, it should be the same. Now if it is same, remove it, what remaining subsequences prefixes we get? We get zk minus 1 and xk minus 1, xm minus 1, yn minus 1. So this zk minus 1 should be LCS of xm minus 1 and yn minus 1. Otherwise, we can increase the length and get better solution. So this is our first observation, that if last elements match, then it is the same, it is also the last element of LCS, and the remaining subproblem we get zk minus 1, it should be LCS of xm minus 1 and yn minus 1. Now second observation. So we can also take a very simple example of this, of first condition. Just take for an example x as BDC, take y as ABC. So here we are observing that last element is matching, and so our this z, so z will be z we can write as, first take LCS of the prefixes. Prefixes are prefixes are BD and AB. Take this LCS, then append the common element C. So Now what is LCS of BD? BD and AB, it is simply B. So we can write this as BC. So this is one example of first condition. Now second and third condition are when the last elements mismatch. So again we can have two possibilities, we will see. So second condition we write last elements are not matching. So second condition is if for both second and third last elements do not match, xm is not equal to yn. Again we can have two possibilities, and these are, just compare zk with, so now zk, it cannot be both, at most it can be one of the two elements. So then if suppose zk is not equal to xm, this xm, then implies that so now the last element of LCS is not, it is not xm. So just remove xm, whatever remains is xm minus 1, the prefix, and for y find the LCS. So we write z is an LCS of xm minus 1 and y. No, correct, y, or we can write this yn. Again we can take a very simple example of this condition. Let's take x as BDCA. Take this x, take this y as ABC. So last elements we have a mismatch, and take for example our z is take it as BC. So the last element of our LCS is not matching with the last element of x. So what we do is simply remove this. What remains is BDC and ABC. So this is the so this A is not in the LCS. So you can safely remove it from x. Now z is still there, BC. So this C, it can match with the last element. There is a possibility that it matches with the last element of y. Actually it is matching in this case. So you cannot remove it. You have to consider it to get LCS. So this is the reason. If it is mismatching with x, just remove it and write this as LCS of the remaining BDC and ABC. Write like this. Now last condition, just the opposite. Again we have this third is, so the last elements are not matching. If xm is not equal to yn, then suppose zk is not equal to yn, implies that z is an LCS of x, or you can call it xm, and the original xm and yn minus 1. So this is the very similar to 2. This time zk is not matching with yn. So just remove yn and see what is remaining is yn minus 1. Take LCS of xm and yn minus 1. So again simple example we take of third possibility. Take x as BDC, take y as ABCB, and take LCS as BC. So this time we see last element of our LCS is not matching with y, no, last element of y. So just remove this, what remains, write it as LCS. So this we can write LCS of BDC and ABC. So this is optimal substructure. I'm assuming, not deciding. This is just an example to illustrate. Yes. Yes. So we are determining the optimal substructure. Problem is defined using subproblems. So here we are not fixing Z. We are taking, so we are assuming various possibilities when last element of LCS, how it compares with the last elements of X and Y, and what are the possibilities, different possibility when we compare last elements of X and Y. Yes. So either we have to take possibility 1 if they match, if they mismatch one of the two possibilities, 2 and 3, we choose the best one. So now next step is we recursively write our solution. We use recursion. So now we get the idea of recursion. Simply choose the best possibility. So depending upon what is the case, if we compare last elements of X and Y, if they match, there is no option. We have to choose the first case. If they mismatch, we have a choice. So we take the best, which gives the best solution. So now we write our recursive solution, step 2. So here we maintain a table, call it Cij. Make a table Cij. So where I and j range from, I can range from 0 up to a maximum of m, j can range from 0 up to a maximum of n. So keeping track of all possible subproblems, now we write recursively. So first, the trivial solution. Trivial solution is when one of the I or j is 0. It means the corresponding sequence is empty. So LCS will be of length 0. So we write our Cij as Cij is equal to, first possibility is 0 if I equal to 0 or j equal to 0. This is the trivial subproblem. Now next we consider first possibility. If xi and yj match, then this is equal to, so just see the first case and write the last elements match, then we have to find LCS of m minus 1 and n minus 1. So in this case just minus 1 for both. So this will be Ci minus 1, j minus 1 plus 1, because we appended the last element. This is the case when if both I and j are greater than 0 and xi and yi are same, xi and yj are same. Now the third possibility is we take the maximum of two possibilities. So write max of, so first possibility is C I comma j minus 1. Second possibility is C I minus 1 j. Max of this. This is the case when if I and j are positive and last elements mismatch. Xi is not equal to yj. So Cij minus 1, Cij minus 1. So this condition is I minus 1j is the second condition, and Cij minus 1 is the third condition. So we take the best of the two possibilities. So this way we make table of LCS values, we compute, and the way we compute is this. Yes, we can also recover. So this is one table. Second table also we maintain. So second table, what we have to do is just see which of the possibilities is giving the optimal solution. So first case, there is no choice, it is already there. Second case, we have to determine by finding the maximum, either this or this. So we should also maintain the path, how to recover. So for this also we maintain a table, call it Sij we maintain. Sij. So here I will range from 1 up to m, j will range from 1 up to n, and Sij is equal to we can say it will store I prime and j prime, the pair I prime and j prime, such that Cij follows from C I prime j prime. So just maintain a pointer so that at the end we can easily recover the LCS. So now how we compute the values? We compute in row major values, row major order. So this Cij computation, Cij and Sij computation. This is in row major order. So row major order means first we start with the first row, left to right, like this, 1 2 3 and so on, 0 0 1 2 3 up to this will go I and j. I is from 1 to m, 1 to n, this will end. Here we have index j, and here we have index I. This will continue like this and so on, and here this will go from 0 1 up to n, m. So row major order means first we start with the first row, fill it, then we start with the second row, and so on, we continue. So time is less, we cannot take a full example. So I will make extra video and upload, and a complete word example I will show. Any questions?